Alright, what up, everyone? Let's get going on this. This is going to be part one of two. I just looked through this thing, and it is 9 pages long. Holy Toledo. We're going to divide this into two parts because I'm not going to be able to sit here for all nine of it at one time, and I don't think you'd be able to either, to be honest. Let's be real. So, we're going to do like four, maybe five, maybe 4.5 pages, and just see what we can do. Starting off, number one. Set notation. Give a sample space for each of the following activities. What sample space means, as a reminder, we start with the letter S and we write a little brace symbol. So it's a little fancy little like thing. If you want to write it in brackets instead, that's cool. So you flip a coin, and if you flip heads, then you roll a standard six-sided die. If you flip tails, your trial is over. So I can get a heads and then a one, or I can get a heads and then a two. I can get a heads and then a three. I get a heads and then a four, a heads and then a five, a heads and then a six, or I could get tails and stop. There you go. There's my sample space. Please note that not each one of these is equally likely. In fact, this letter T over here happens exactly half the time. And you could think about it, each one of these is going to happen 1/12 of the time. If you want to think about that, you don't have to know that right away. Just continue on, same exact idea for these ones. We're looking for sample space, and you're just selecting two numbers from 1 to 5. Numbers cannot be repeated, and the order of numbers does not matter. So for instance, I'm able to have a 1 2, or a 1 3, or a 1 4, or a 1 5, or a 2 but not a 1, or a 2 2, because they can't be repeated. So 2 3, 2 4, 2 5. I can have a 3 4, a 3 5, or a 4 5. Remember, if you're struggling with any of these types of questions, what you're able to do is to make a tree, and in other situations, you can also make a little boxes like this one, because you're drawing out of a hat and without replacing to form a three-letter password. So like this one, I guess you can't do that. You can do that for the size. Let's just write the whole sample space out. So for instance, I could have x, y, z, or I could have x, z, y, or I could have, what else could I do? So that's starting with x's, or I could start with y's, y, x, z, or y, z, x, or now starting with z's, z, x, y, and zyx, and that is all of them. That is all the possibilities I could have for a three-letter password. That's a pretty weak password, by the way. So anyways, if you need help with these, you could always do a tree. So I will do that tree for this one. You couldn't really do a tree too well for this one, but I could do a tree here where I could have like heads or tails. And if I got heads, then I can get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. But if I got tails, then I stop. So that might help you make the whole thing if you're struggling with this concept. You don't need the tree. Trees are optional. A license plate number is created with 3 letters, followed by 4 numbers. Letters cannot be repeated, but numbers can be repeated. Hoof. So letters cannot be repeated, but numbers can be. A license plate number is randomly created. So 3 letters followed by 4 numbers. So if letters cannot be repeated, then we have 7 boxes total. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay, so 26 letters for the first option, but you can't repeat letters, so it's going to be 25, and you're going to have 24. And then after that, you can repeat numbers, any numbers at all. So 10 digits. There are 10 possible numbers you can put. So you have these guys all multiplied together. If you end up multiplying this out, go ahead and do so. I said in class I don't really want to, but I think it will be easier for me to grade if we have all of them multiplied out, but I'll probably still give you credit if you don't. 1, 5, 6, and then 5 zeros. 1, 2, 3, 4, 5. All right, cool. 50 people in a contest. 5 are randomly selected to get these different prizes. So if you use the box method, that's all well and good, and that will work for you. However, after I write this out, I want to talk about the fact that we could have used a lesson from earlier this week. If we notice, this is something where order matters. We're choosing 5 where order matters. So in our calculator, this is 50p5. So you don't have to write all this out. You can just write 50p5. Honestly, I'd probably give full credit for that. If we need to type this into the calculator, we have 50 math PRB 5, and that's going to be some holy Toledo number. 254 251 200. 254 million different places. Or different ways. Places. I didn't even say a word right there. My brain is not operating at full capacity, guys. This is why I'm not going to do the whole packet in one night. For real, though. Number 6. A multiple choice test consists of 10 questions, each having the options A, B, C, or D. You randomly guess the answers to the questions. So it says the size of the sample space, so it's not like the probability of getting it right. But because every single one has 4 options, you have 4 things to choose from 10 times. So 4 to the 10th power is all we need. So 4 to the 10th. That's going to be 1048576. So 1,048,000. And by the way, the probability of getting 100 by guessing would be that number. That's 0.0000009. That's a lot of zeros. You're just not going to get it right just by guessing. All right. So finding these Venn diagrams and the complements. Let's see it. So rolling 2 standard 6-sided dice. Rolling a sum that is less than 8. And the complement. It says describe the complement. Doesn't actually say find the probability. Great, I don't have to. So avoid using the word not and other variations of not in your answers. So rolling a sum that is less than 8. The opposite of this, we could say something like rolling a sum 8 or more. Easy enough. Rolling a sum that is at most 15. Well, that's kind of a silly event. I mean, I guess I could say that at most 15 is 14 or less. I mean, I could say 14 or less. But what a stupid event, because we're rolling 2 standard 6-sided die. 12 is the biggest we can get. So the wait, 14 or at most 15, 14 or oh boy, 16 or more. I said it wrong. I was so interested in saying how stupid this question is. You can't have that. You can't even be up to 15 anyways. You only get up to 12. I don't know why they're asking this question, but 16 or more is fine. Whatever. So draw 2 cards from a deck of cards. Both cards are the same suit. So instead of saying both cards are not the same suit, cards are different suits. Different suits. Okay. Opposite. At least one of the cards is the king. None of the cards are a king. None of cards king. That is such great English. I should be an English teacher with none of cards king. Oh my gosh, you guys can't even see the bottom of this. I apologize. It didn't really matter. I guess I was just talking through those. Whew. Alright, calm down and move on to the next page. I'm supposed to do some shout-outs here. I think the first shout-out is to my man Jacob Mario Lemieux Kaufman. Absolutely wonderful singer. Heard his voice out in the choir competition. He is just wonderful at singing. He also participated in nice little singing during my class, and we did some little karaoke. He's a great dude. Does need to work a little bit harder sometimes, but he is overall just a really nice and awesome guy. So let's do this next problem now. Determine the size of the sample space for each activity, list all the outcomes of the given event, and find the probability of the event. So we roll 3 standard 6-sided die. Describe the size of this activity sample space. So we roll a 6-sided die. There are 6 possibilities first, 6 possibilities second, 6 possibilities third. We've already talked about this, I think on the previous video actually, and then someone made a whole meme out of it. But there's 216 possibilities. Great. Number 9, event rolling a sum that is at least 17. So you really got to figure out how you can even get to a 17. This is tough. But the outcomes for this event that work for having a sum of at least 17, I could do a 6, a 6, and a 5. I could also have a 6, a 5, and a 6. I could have a 6, a 6, and a 6. I could have a 5, a 6, and a 6, because this is 18, by the way. These add up to 17, these add up to 17, these add up to 18, these add up to 17. Or I could have... Is there anything else? Are those just the possibilities? I think that's it, right? The 5 was in each of the 3 spots. And the 6. Honestly, the question is not going to be as hard in the test, but the point is there are 4 different ways to do this. So the probability of rolling a sum that is at least 17 is going to be 4 divided by 216, and therefore the probability of rolling one that's less than 17 has to be 212 divided by 216, the complement of the event. What a nasty problem. Oh well. Flipping a coin 4 times and getting exactly 2 heads. So flipping a coin 4 times, size this as activity sample space. We should actually know what this one is. We're flipping a coin 4 times, so we have a 2 and a 2 and a 2 and a 2, and get 16 here is the size of the sample space. But the probability of getting exactly 2 heads is not exactly the easiest. So the probability of getting exactly 2 heads, we actually have to write out every single little possibility. You might want to do your whole tree thing where you do tails and heads and tails and heads, and you do the whole thing out. I'm going to write all the possibilities right here. So we have heads, 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 tails. And then we have heads, heads, tails, heads. And then we have heads, tails, heads, heads, and tails, heads, heads, heads. I don't know if you can see how I'm doing this kind of in a methodical fashion, but I am doing my best to get it all the way there. So we have tails, 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 and then we have tails, 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 heads, tails, tails, heads, tails, tails, heads, tails, tails, and heads, tails, tails, tails. Alright, so what I've done is I took care of all the ones that have only heads, all the ones that have only tails, and then I took care of the situations where you have exactly 3 heads, and there are 4 of them here, and then there are 4 of them that have exactly 3 tails, and now I'm going to start doing the ones that have 2 heads and 2 tails. So now we have a heads, heads, tails, tails. We have a tails, tails, heads, heads. And then we have a heads, tails, heads, tails. Then we have a heads, tails, tails, heads. We have a tails, head, tail, head, and finally tails. What did I miss? Tails, heads, heads, tails. Hopefully we actually got 16 here. We got 5 and 5 and 6. Add to 16. Beautiful. We found them all. So the outcomes for this event that work here. These 6. I'm not rewriting them. Boom. Right there. Probability of flipping exactly 2 heads must therefore be 6 over 16. And getting any of the other results here must be 10 over 16. Hopefully nothing that long in the test, because I don't feel like grading that. I'm going to be honest. It's going to take forever to figure that out, but I don't remember what's actually there on the test. Hopefully it's not like that, though. What a disaster. Number 11, rolling a multiple of 3 equals 1/3 when rolling a standard 6-sided die. If you roll a die 200 times, what do you expect to happen? Well, you just multiply that 200 multiplied by 1/3, and if you do that in the calculator, 200 times 1 divided by 3 there, that's going to be 66.6 repeating, so this is approximately 67. So you said you expect to get around or near 67 multiples of 3. Easy enough. Using proper notation, give the probability space. So probability space is the probability of every single thing that can happen along with what could actually occur. So we're going to write P of the different possibilities. So we can give red jelly beans, we have P of yellow jelly beans, P of green jelly beans, P of purple jelly beans, and there are 10 and 20 and 30 and 40 all mixed in a bag. So all of these have a division by 100 as their probability, because those 4 numbers there add up to 100. And, well, there are 10 red ones and 20 yellow ones and 30 green ones and 40 purple ones. That is like the easiest question ever. You just got to fill it out. The spinner is spun once. Honestly, the question is not going to look like this in the test because you can't really tell like what size all these things are. Is like, well, is that size? Is this the same as that? Is that the same as this? But, you know, I'm just going to try it out. I'm going to pretend that this divides into half evenly, right? And this divides it into 3 parts evenly. So there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 parts total. So then we have the probability of getting an A, we have the probability of getting a B, we have a probability of getting a C, and these are all going to be divided by 12. And then how many are there? Well, there are 1, 2, 3, 4, oh, there's also a D on there. Oh, God. Let's talk about missing points. I don't even notice all the letters. All right, 1, 2, 3, 4 A's. 1, 2, 3 Bs, 1, 2, 3 Cs, and therefore 1 D. That doesn't even add up correctly. There are 4 C's. I can count. 1, 2, 3, 4. Jesus. All right. Issues, issues, issues. Moving on to the next page here. So second shout out. I forgot all the people who actually wanted me to give them a shout out, so I apologize in advance if I forgot who wanted a shout out. But I do also remember that Momo and Kira in the back there, they wanted a shout out. They're usually pretty funny. They get their work done like weeks in advance, and then they have nothing to do in class, and I guess that's okay, but because they get their work done. But I don't really know. They're awesome. I love them. Lots of fun in the back there. Cool stuff. Next one. P of A equals 12 divided by 7. That's not possible. No possibility. Not possible. And if not, state why. P of A, we know this thing. All probabilities must be between 0 and 1 strictly. This would mean it happens more than always. So, yeah, not possible. So anything that's over 1, not possible. So that's a check mark. Anything negative, not possible. Not possible. And definitely possible. That means it doesn't ever happen. Drawing a Venn diagram. You know, honestly, I'm just not going to draw a Venn diagram. It's just not going to happen. You got Venn diagrams later over here in the packet, I think, somewhere. Like, boom, Venn diagrams over there. We'll deal with them later. I'm not drawing any of them, so forget it. Forget it. We want the probability of things happening. So draw a single card from a standard deck of cards, and the event is drawing a face card, and the event is drawing a club. So the probability of drawing a face card. Well, it turns out there are a grand total of 12 face cards in the deck because there are 4 jacks, 4 queens, and 4 kings. So there are 12 over 52. Maybe I should write this all up on the side here, all the different things. There are 52 cards in the deck. There are 26 red, 26 black. There are 13 hearts, 13 spades, 13 clubs, 13 diamonds, and there's exactly one of each one of these has exactly 1 ace, 1 2, 1 3, all the way to 10. So ace 2 3 4 5 6 7 8 9 10. There's like 1 ace of hearts, 1 3 of clubs, 1 10 of diamonds, etc. And then a jack, a queen, and a king. So there are 13 hearts, and these are the 13 hearts, all 13 of those. Whatever. Probability getting a club is a 13 out of 52. Probably getting a face card and a club at the same time. Well, there are 3 face cards that are clubs. Probably a face or a club card. A couple ways to think about this. My preferred way is just to use the formula. The formula says that the probability of 2 things and their intersections, the things happening at the same time, the probability of their union, which is, by the way, the or. This word means or, so probability of or is equivalent to the 2 things added together minus the probability of their intersection. And that guy means the word and, by the way. So this probability here must be 12 over 52 plus 13 over 52 minus 3 over 52. So that's going to be a nice little 22 out of 52. And not a face or not a club. Oh boy, so now we got to do the same exact... Oh boy, you couldn't even see that again. I apologize. That's the second time this happened in this video. I'm cut from the team. So not a face or not a club card. Well, the opposite of that is going to be... we got 40 over 52 because I'm adding these up. Not a face card must be the opposite of that. Not a club card must be the opposite of that, which is 39 over 52, minus not this guy, not the and of the ors there, which has got to be, oh boy, what is that? 49 out of 52. So what's that? 79 out of 52 minus 49 is 30 out of 52. So yeah, obviously not this one, not face or not club. Did I do this right? I'm gonna write little notes to myself off to the side here. You can ignore them for a second, maybe take a little break, chill for a second. But I'm saying not face or not club. That's got to be equivalent to not face intersection club. I think this is what they intended you to do on this problem, but I think what the actual answer to this question is this, which we did not teach in class. This is called De Morgan's Law, that you can like factor out a knot out of two things. And the knot of the intersection is 49 out of 52. I don't know what they wanted, but I'm not asking this on the test anyways, and if it was asked on the test, I'd take it off because we didn't learn it. So we can just forget about that problem and move on with our lives. I'm pretty sure that's the real answer to the question is 49 out of 52. I think this is what they wanted you to do in the problem, but I didn't write this review packet. I'm done whining. Okay, probably the same color. We got these two marbles coming out and two red marbles, two blue marbles. Pick them mixed up. Two marbles are drawn at the same time. The order that the marbles drawn does not matter. Probability that you end up getting exactly the same color. Well, you have to get the first color you draw is not relevant. If you draw a red one first, whatever, that's fine. But let's just pretend. So we draw two from a bag. All right, you know what? We're gonna write these things. There are two ways to do this question. You could draw out the entire sample space for the entire thing, which I don't want to do because I don't like writing all these things out like I did for these heads, tails problems, but you could do that. You could write every single possibility. The first one is red, and the second one is blue, and the first one is red, and the second one is red. Blah, 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 blah. You could write out all these different possibilities of what you could get. For your marbles, there's going to be a whole boatload. In fact, there are going to be 12 possibilities because you have 4 times 3 for the possibilities here. I don't feel like writing all 12 of those out, but the probability that they're going to be the same color is the probability that you draw the same one. So after you've drawn one marble, there are 3 marbles left in the bag, and there's only one of those marbles that is the same color. So the probability of the same color must be 1/3. A probability that a blue is drawn, period. Well, the probability of a blue drawn period must be the probability of not drawing 2 reds in a row. So the probability of not drawing 2 reds in a row, let's figure out what the probability of drawing the 2 reds in a row is. Well, the probability of drawing the 2 reds in a row must be 1/2 to draw the first red, and then 1/3 to draw the second red, and that's going to be 1/6. So that's your probability of getting all reds. So the probability of getting at least a blue must be 5/6. Again, I could have actually just written out every single possibility here of what could happen. But I don't really want to do that. If you want to do that, you knock yourself out. You will end up having 10 combinations that have a blue and only 2 combinations that have only red. By the way, the only combinations that have red would be red 1, red 2, and red 2, red 1. So you could figure out that that guy right there is 2/12. And therefore 10/12 for the possible blue answers. I don't know. Probability that both of them are blue. Well, we just probably that both are red. It's the same exact probability. It's going to be half times or 2. Let me write it all the way out. 2/4 times 1/3, and that's got to be 2/12, which is 1/6. Again, we just did this one. Blue is drawn, or the colors are not the same. So the probability of a blue one being drawn here, we just did this one, is 5/6. The colors not being the same is probably the same color is a third, so colors are not the same must be 2/3 minus the times when the blue is drawn and the colors are not the same. So blue is drawn and colors are not the same. How often? Well, all the times except when it is both blue. So the probability of both of them being blue is 5/6. Probability of them both being blue is 1/6. And they have to have colors that are not the same. So how many of them? So it also means that 1/6 of the time you have all reds. So colors the same here, like a blue. Colors the reds over here, red. Don't like that either. So the and part of this is -4/6. As a reminder, you can do all these in your calculator, and the questions are not going to be this hard. I can't believe it's actually this difficult of a question, to be honest. I don't even like this problem. I think I'm just going to do these in class. -4 divided by 6. You get this 0.833, which is acceptable as an answer. Okay, and you can also hit math enter, enter, convert that to a fraction, you get 5/6. Let's make sure. And that makes perfect sense, because the blue is drawn, or the colors are not the same. The opposite of that would be they're both red, so 1 minus that. Blue is drawn, or the colors are not the same. That's the same question. What? I don't even know, guys. I hate this page already. I should just like say skip page 13, you know, for real. All right, let's move on. So if A and B are independent events, then P of A equals a given B is the same thing as the P of A, and the P of B given A is P of B. And that's because knowing B happened doesn't change probability of A, and knowing that A happened doesn't change probability of B. That's a definition of independence. Which of the following would you have to have a bigger value explain? Probability that it will be cloudy, given that it will be raining. Well, if it's raining, it's almost certainly cloudy. I mean, there are a few times, I guess, when it rains without clouds, but that is not an often occurring thing. The probability that it will rain, given that it will be cloudy. I mean, that happens, but it doesn't happen that often, so definitely this one. If it's raining, it's probably cloudy outside. That is a high probability. So this one by a long shot. Anyways, let's do this one. Finally, some conditional probabilities that actually make some sense here. So, based on your answers, are they independent, dependent, whatever? So, drawing a heart and drawing a face card. First of all, we actually know in advance that we can just say that these are dependent probabilities. Actually, I lied to you. They're independent probabilities. I'm going to try to explain why in a second. Okay, probability of drawing a heart, 13 over 52. Probably, which is reduces to 1/4, by the way. You actually want to reduce these for some questions, or at least approximate them in your calculator, so put that 0.25 down. Probability of heart, given that you've drawn a face card. So first of all, there are 12 face cards in the deck. How many of those face cards are hearts? Well, that's going to be 3. That is also 0.25. Because these numbers are the same, check mark, we would say independence. I read it incorrectly the first time, which is why I thought dependent. I apologize. Probability of drawing a spade here, given that you've drawn a black card. Ooh, now we can see, is this the same? I don't know. So probability of drawing a spade period is 13 over 52, which is 1/4. Again, that approximately 0.25. Probability of drawing a spade, given that you've drawn a black card. Well, now that you have black cards, there are only 26 black cards in the deck, so your denominator has changed. Note that that second thing changes that denominator again. So the probability of spade, you have your black card, is, well, half the black cards are spades, so that's going to be 0.5 instead. So now we say dependent because these things are not the same. Knowing that one has happened changes the probability of the other happening. Number 26, the probability of rolling a sum of 7 is going to be 1 divided by 6. It's very useful just to memorize that number so you don't have to worry about it so much. But if you actually wanted to go through this, you have to make that whole dang little chart. You got to go 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, you know, and fill this whole thing out. You know, just make this whole dang table. You got a 2, you got a 3, you got a 4. Bleh. Point is, there are 36 possibilities here, and 6 of them add up to 7. You can have a 1 and a 5. Sorry, 1 and 5 do not add up to 7, that adds up to 6. You have a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. 6 different possibilities over 36. Now, if you don't like that, here's a nifty little trick to memorizing these like things. If it makes sense to you, use it. If it doesn't make sense to you, you know, do something else. Here's my little trick to doing these rolling the two-sided die thing. I'm going to write the numbers that are possible. So you're rolling 2 dice and you're getting the sum. Here are all the numbers that are possible. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And how many ways can these things come up? There's only one way to get a 2. You have to get a 1 and a 1. There are only 2 ways to get a 3. You can get a 1 and a 2, or a 2 and a 1. To get a 4, you can get a 1 and a 3, or a 3 and a 1, or a 2 and a 2. That's 3 different ways. You might actually notice a pattern right now. It goes 1, 2, 3, 4, 5, 6. However, be careful, because on this side, 12, there's also only one way to get a 12. There are 2 ways to get an 11. There are 3 ways to get a 4, 4 ways to get this, 5. So it goes 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. There are 6 divided by a total of 36 ways to get a 7. There you get that. All right. What's probably getting 7, given that one of the numbers is a 2? So if one of the numbers is a 2, that's a little bit different. That one you really want to go through that whole table and figure out. So one of your numbers is a 2, so you know these are your only possibilities. So how many different possibilities are there? So let's just like jot them down really quick. You can get a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, a 2 and a 5, or a 2 and a 6. You could also have a 1 and a 2. Don't write 2 and 2 again. You already wrote it down. A 3 and a 2, a 4 and a 2, a 5 and a 2, a 6 and a 2. This one you actually do have to write out. There's not really a good way of doing it. Now, how many of these are a sum of 7? Well, this guy is a sum of 7, and this guy is a sum of 7. None of the other ones are a sum of 7, so there are 2 possibilities over a grand total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 2 elevenths. If you rolled one of the numbers is a 2, 2 elevenths chance here of getting a 7. This doesn't seem right. I'm going to think about it for a second. I want it to be 1/6. One number rolled is a 2. Did I write them all down correctly? 2, 2, 1, 2, 3. Yeah, I wrote them all down. Did I find all the ones that add to 7? Definitely 2 and 5 are the only ones that add to 7. Yeah, that must be the right answer. Anyways, therefore these guys must be dependent because they're not the same probability. Dependent. I really thought they would be independent. They're not dependent because we're saying at least one of them is a 2. So this guy right here is screwing this up because the 2, 2 can't replace it twice. That would make it dependent. Huh. I'm going to think about this one for a second before we actually move on. So I guess you guys can pause in the video. Maybe this is a good time to end the video. How many pages do I have left? I got 1, 2. So how many pages have I done? I said I was going to do 4 to 4.5. So I've done 1, 2, 3, 4. I have to do 4.5 to 5. So I got to do more. I'm going to think about this a little bit more. So this is a good time to take a little coffee break, maybe do another little shout out here. One more student I remember definitely did want a shout out was Doreen. She is also awesome, very fun, works very, very hard in my class on occasion, and then some days doesn't really do anything, but she ends up working very hard before the tests, and I'm very thankful that she does work so hard so she can get her high grades. Proud of her for sure. What else is possible? I'm going to think about this just a little bit longer. Is there an answer key attached to this thing? No. I think there is an answer key somewhere on my computer. So I'm going to just go ahead and look up an answer key really quick. Make sure I did this question right. See if somebody else did it already. And if someone hasn't, then life goes on. I think I'm just too tired to be doing this, guys. I've been making these videos for quite a bit now. Let's see. We got email, sign in. I'm looking for mod 10 stuff. So mod 10. Mod 10 probability review key. Open the file. Where are we at here? Let's see if this agrees with me. 2 11ths. The other teacher got the same thing. I don't know. I'm like confused like mentally on this one. I thought for sure I was good, but whatever. I'm gonna move on in my life. I got the right answer, and we're going on to the next question. Rolling two stick standard dice. Roll are the same number. The first die lands on a 5 here. So if the first die lands on a 5, and the rolls are the same number. So the rolls are the same number. This is obviously 1/6. Not 1/6. I am so sorry. Is it 1/6? Rolls are the same number. So you get a 2/2. Like 2/2, 3/3, 4/4, 5/5. Yeah, it's 1/6. 6 out of 36, which is 1/6. 1/6 of the time you'll get doubles. The rolls are the same, given that the first is a 5. Only 5/5 will work. But if the first is a 5, the first number is a 5, right? So the other possibilities here, you can actually just write them all out. 5/1, 5/2, 5/3, 5/4, 5/5, 5/6. Again, 1/6, and therefore these must be independent events. All right, moving on here. The last page that I'm doing, then we'll do the Venn diagrams tomorrow. Ooh, I like these two-way tables. These two-way tables are cool. All right, so first of all, two-way tables are awesome because they just make sense. You know, you get the 180 and the 120 added up. We got totals here. That's going to be 300. These got to add up to 300. So 300 minus 20, 220 has got to be 80. And then, you know, these guys got to add up to 180. So what number plus 126 is 180, well, that's got to be 54, and we can double check them all the time. 54 and 26 is 80, so we're good to go there. And then we got to figure out what number adds up here. I believe we're going to get 94. Double check here. 126, 94 is 220. Awesome. Probably the A occurs period. Well, probably the A occurs period is that number 80 divided by the entire thing. Probability of A and B occurring at the same time. Well, event A occurs here, event B occurs here is 54 over the entire thing. Please note, for all of these that do not have a given bar, we're using 300 on the bottom. Probability of A or B occurring. Well, probability of A occurring is 80, right? Over 300. Probability of B occurring is 180 over 300, and we just calculated the probability of both of them occurring, which is 54 over 300. Got to go ahead and subtract those up. What's that going to be? 260 minus 54 is 204? Did I do that right? 260 minus 52, 206. I can add, oh my god, I really got to go to bed. 206 divided by 300. Awesome. Probability of B, given that A has occurred. So the probability of B, given that A has already happened. So if A has already happened, that means that our denominator is now 80. The probability of, because A has occurred up here, so boom. And our event B happens 54 of those 80 times. Probability of B happening, now my denominator is 180. And my numerator is, again, A occurring. Or A occurring, this is B occurring, so 54 over 180. So are events A and B independent or dependent? Well, because the probability of A is 80 over 300, we actually need to go ahead and reduce this and get us our little reduction there. What's that going to be? It's going to be 8 over 30, which is 4 over 15. We also need to now reduce this 54 over 180 and see if it's also 4 over 15. I don't know why I wrote approximately. It's exactly equal to. So 54 divided by 180. Let's just use a calculator. Let's cheat to reduce this fraction. Well, actually, it did it for me there. 0.3 is 3/10. So these must be dependent. Showing the work here, the probability of A and B is equivalent to this. Probability of A and B up here is 54 over 300. Probability of A occurring, we wrote that as 80 over 300. Probability of B, given that A has happened, is 54 over 80. 80s cancel, check mark, good to go. And you know what? We're going to pause there. We'll finish this up on the next video. We'll do that tomorrow night. Sorry, guys, but I am heading to sleep. Too tired. Peace.